start. It's a great pleasure to talk about my work. Actually, it's a collaboration work, on the wave-particle resonant interaction and their contribution to the radiation belt electron dynamics and the coupling between the Earth's magnetosphere and ionosphere. First I would like to acknowledge my, let me turn the pointer mode. First, I would like to acknowledge my collaborators listed here for their contribution to this work. This is what I will try to cover in today's presentation. Let's start from some brief background. So what is space physics, actually? Before this, I want to mention that I will mainly talk about three phenomena involved in this study or in this presentation. Without covering too many details in space physics. The three phenomena I will talk about mainly focus on them. First, what they are. Second, where they are. And the third is their characteristics. So let's start from some background on the space physics.
What is now joining?
I'm sorry, somebody joining, so I got some sound in my side. So the first thing is, what is space physics? So basically, this is a very big topic. I know that Professor Lopez actually have a graduate level course covering this subject for an entire semester. So we certainly will not try to cover every detail here in this 1 hour presentation. But I would like to focus on a couple of important concepts before we start talking about our work. So specifically, my study focuses on the area between the sun and the Earth's upper atmosphere. So, but in general, I know space physics studies the entire plasma system within the solar system. So, by my studies, basically focus in this region. But interestingly, this region is not as peacefully as this picture shows. In reality, this region is quite dynamic. It's immersed into continuous streams of charged particles emitted by the sun, and which we call it the solar wind, just as opposed to the regular wind we have in the atmosphere. And it is the Earth's internal magnetic field that forms such kind of cavity to protect us from these dangerous particles to the human being, which we call this entire region the magnetosphere. And here is the scheme of the Earth's magnetosphere in more details. And here's the sun, the solar wind flowing this way, and this is the Earth's magnetosphere. Like we said that the magnetosphere is formed by the interaction between the solar wind and the Earth's magnetic field. Because of the solar wind, the magnetosphere is not exactly dipolar for a dipole moment. It's more like compressed on the day side and stretched on the tail side, which we call this region the magnetotail in general. Magnetotail will be the first region that we will talk about today. So generally, it can extend all the way to greater than 100 Earth radii towards this direction. But our study focuses on this specific region much closer, actually, because that's where we can see various plasma dynamics related to the reconnection. And also, we still have some active coupling between the magnetosphere and the ionosphere. That's one focus of my work here. I will talk about later. That's pretty much about the magnetotail. I forgot to mention that because of this all sorts of plasma dynamics in this magnetotail region, there are various waves to be generated by these dynamics. And also these waves will scatter these magnetospheric electrons to be lost into the upper atmosphere to form the aurora. So this kind of coupling we will also talk about in today's work or in today's presentation. I guess that's the first topic I want to cover. And the second topic is about radiation belt. Basically, radiation belt is just two zones of high energy particles trapped in the magnetosphere. The inner belt, which is closer to the Earth, of course, is more stable. The outer belt is highly variable, actually, as a response to the activities that we just mentioned in the magnetic tail, and also as a response to the local plasma waves. So radiation belt is an important region to us, basically because lots of navigation and communicational satellites are operating there. So we want to better understand the dynamics to protect them. And the third topic we want to briefly introduce is the diffuse aurora, which is basically a type of particle precipitation from the magnetosphere to the upper atmosphere, or more precisely, the ionosphere. So this is a result of the particles being scattered by the waves in the magnetosphere. So among all types of auroras, diffuse aurora actually, although they are pretty weak in intensity, but they provide the dominant energy input into the ionosphere. That's why we care about it. So these three phenomena, after we introduced them, we noticed that they share one common characteristic, is that all of them involve the waves. So specifically, as a response to the magnetic tail dynamics, it's illustrated here, the deposition front and the fast plasma flows. Various plasma waves can be excited, including the kinetic alpha waves, the Western mode waves, and the electron cyclotron harmonic waves. These two, the Western mode and ECH wave for short, is what we will focus on in today's presentation. Both of them are actually electron scale waves with a difference in the frequency range, actually. That's pretty much the background. I think that's enough for you to probably understand what I will talk about later. So then let's talk about the data. As we know, in my perspective, space physics is a subject, or is a topic heavily built up on measurements in space. Here are a list of main missions I've worked on before or now. So especially the THEMIS and the Violent Probes mission, which this the work I will talk about today heavily rely on. And also I've been working on a mission called Alpha, which is a CubeSat mission, actually, a smaller size satellite. And also a mission called Juno that went into the Jupiter's magnetosphere. But these parts are not covered in today's presentation because of time constraint. Because this is an online presentation, I'm not sure whether you have any questions at this stage.
We'll have questions at the end.
Okay. Yeah, sure. Then let's continue. Then let's look at the results in three parts. That's the exciting part, actually, for me. I would like to mention that because of time constraint, again, I will only cover the most noteworthy results or significant results. But if you are interested in the details, feel free to talk to me about it afterwards. The first part is about the interaction between electrons and their Western mode waves. And in this part, we will talk about, again, make a brief introduction to this subtopic that I think will be necessary and relevant to this work, because previously we only mentioned some very general background about space physics. And of course, we will talk about the results, most exciting one. And then in the end, I will try to summarize it in three aspects. First one is the direct advances of our work in each of these parts in the understanding of a specific topic. And the second aspect is the implications of our work on future works. And the third, we will talk about the contribution of our work to the CUSIA Center here. And let's start from some brief background again. The picture that we showed before about the radiation belt is actually, I would say, I more or less idealized the picture because in reality, we know this radiation belt is marked here by the purple shades are actually quite dynamic. It constantly swell and shrink in response to the solar wind activity, or more directly to the magnetic tail dynamics. So because of this radiation emitted by these high energy particles, radiation belt can act as a natural hazard to the satellites within. So that's why we need to understand their dynamics. And interestingly, these dynamics, probably surprisingly for you, but interesting for me that these dynamics are heavily contributed by the wave-particle interaction processes in this region. Yeah, that's the background. A little bit more. Depending on the wave amplitude, different regimes of wave-particle resonant interaction can be triggered. This figure, let me show. It's a little bit busy figure, but we can walk through this quickly. This figure shows the variation of pitch angle and energy for a certain particle after they interact with plasma waves. Specifically, here is the Weisler-Mode coarse waves. We can see that at low wave amplitude, the interaction is mostly diffusive, which means that there's no average change in the pitch angle or in energy, just the diffusive terms. As the wave amplitude increases, as we can see in the later two panels, we start to encounter this nonlinear scattering and nonlinear trapping. This is just the terminology. You don't need to pay too much attention. It's just you need to mention. I just want to emphasize that whenever the nonlinear effects are triggered, we do start to encounter large changes in the pitch angle in the average sense, right? And also, interestingly, for the nonlinear trapping, we see very efficient energization of these particles. Actually, the pitch angle variation is related to the energy in this sense. Yeah, that's pretty much it. Just means that the nonlinear effects can trigger more effective energization and scattering than the quasi-linear diffusion. That's the main point I want to deliver here. And in terms of the relative importance between quasi-linear and nonlinear wave-particle interactions, actually there's it's still ongoing controversy. Actually, the quasi-linear approach, on one hand, has been widely adopted to explain the observed dynamics in the radiation belt electrons, especially those on relatively long time scales. But recently, interesting, it has been shown that a significant portion of these waves can be strong enough. You see, this can approach hundreds of millivolt per meter to trigger those nonlinear effects we just talked about. And also, a few of particle observations have indicated that the very fast particle flux increase in a certain energy range resonant with these waves, but in a very short time scale, within 1 hour, that this time scale cannot be explained by the quasi-linear effects, basically. That indicates the effect of nonlinear wave-particle interaction in reality. So this raises a question, actually, how important are the nonlinear effects in the radiation belt dynamics overall? So that's what motivates our work here. We will try to quantify the occurrence rate of nonlinear Weisler-Mode waves here using about 8 years of valence probes and Themis observations. So yeah, let's just look at the results strict. What's this plot? The color coded is what we are after for. Is the occurrence rate of nonlinear Weisler waves with respect to the total, the general Weisler waves in general. All the Weisler waves in general. And the x-axis is the electron pitch angle, and y is the electron energy. So basically, we separated it for radiation belt, and this is more generalized magnetic tail region. So we can see that in general, the same for these two regions, the nonlinear Weisler waves can occupy up to 10 to 30% with respect to the total Weisler waves. This number is actually surprisingly high to us because previously we only observed a few or less than 10 acceleration events that can be attributed to the nonlinear Weislers. So people would anticipate that there's not much waves being sufficiently to trigger the nonlinear effects. but this number 10 to 30% is actually very high. It indicates that probably there are other reasons that we cannot see these nonlinear effects directly from the data with a matching occurrence rate of 10 to 30%. So a natural question is that what are these parameters that reduce the efficiency of these nonlinear wave surveys that we should have seen in the particle data as well? What we found in our result is that it is actually the wave packet size that is doing the job. So what is wave packet size? Basically, the waves doesn't come with infinitely sinusoidal waves. It comes with a train of different sizes, a train of wave packets with different sizes. Here we define it as the number of wave period in one wave packet as the wave packet size in y-axis. What's shown here is the distribution of our data set in the wave packet size versus wave amplitude domain for these two regions of interest as well. And we found out that from our data set, that most of these wave packets propagate as very short wave packets with a wave packet size less than 10 or 20. It actually has been shown before in simulations that these short wave packets can significantly suppress the nonlinear effects of these intense waves. But what we show here is actually the first observational evidence of it from a statistical point of view. So this is convincing me enough that it is the wave packet size that does the job of suppressing nonlinear effects. Okay, that's probably too much details, but let me just summarize it for the first part. Our work directly explains one of the long-standing dilemma in the wave-particle resonant interaction study, which is between the high occurrence rate of high-amplitude waves and the very few observations of nonlinear acceleration from the electron point of view. So this is the immediate advances for our understanding on this problem. And the second one is that in addition to the wave amplitude, we also surveyed the characteristics of this intense, what we call the nonlinear wave surveys. This is actually critical for future radiation belt models to properly incorporate these nonlinear wave surveys into future radiation belt models to properly model or predict the radiation belt dynamics. This part of work is in line with one of my funded NSF grant, and also I submitted two new NASA proposals on this topic as well. And then in terms of contribution to COSIA here, as you can see that the amplitude of these waves can easily trigger the nonlinear wave-particle interaction. So in order to properly model the electron precipitation or ionospheric conductance out of this process, ideally we will need to incorporate the nonlinear scattering effects into our precipitation or conductance model that is still missing in the present models. That's pretty much it for the first part. The second part is about the wave-particle interaction between ECH waves and the electrons. Let's start from some brief intro. As we know that the diffusor constitutes about 80% of the total precipitating energy input into the ionosphere. But interestingly, although its origin has been attributed to the wave-particle interaction process from either Wessler waves or ECH waves, but whether the relative importance of these two wave modes in driving the diffusor actually are incontrovertible for the past 50 years, I would say. And then about the modeling efforts on the precipitation of diffuse aura, there has been empirical models between the precipitating flux and the solar wind activities. Parameters raised as the average solar wind quantities. But these models are actually not ready to be applied to the global MHD models. That's why here we are motivated to build an improved precipitation or more directly conductance model by modeling the wave-particle interaction process directly driving this diffuse aurora precipitation. In this part, I want to mention that we'll only talk about ECH waves, but similar efforts have been applied to the other wave mode, which is the Wheeler mode waves. Yeah, so for a typical ECH wave amplitude, their interaction with the plasma shade electrons or magneto tail electrons falls into this so-called quasi-linear regime. So that's why we can adopt this more or less standard quasi-linear diffusion equation to model the evolution of the wave particle interaction process, will this lead to the precipitation flux. Okay, from this equation, we can see all we need to do is to quantify this so-called diffusion coefficients as a result of ECH wave scattering. And because of these coefficients actually depend on the wave characteristics, most important, the wave amplitude. We first look at these wave properties in the magneto tail measurements. So here is a superposed epoch analysis of ECH wave amplitude down at the bottom as a response to depolarization fronts and plasma injections from the magneto tail. We can see that almost immediately after this magneto tail dynamics, we see a rise in the ECH wave amplitude. And also, we survey the occurrence rate and the duration of the ECH wave ECH waves themselves. And then we have a well-established diffusion code to incorporate to estimate the diffusion rate based on this observed wave properties. Just as shown here as an example, the pitch angle and the energy diffusion rate from the ECH waves at a certain space, certain location. From this, we have this diffusion rate so that we can model this precipitating electron flux directly using our quasi-linear diffusion theory. So the red line is one example of our model, the precipitating electron flux as a function of energy, of course, depending on the realistic wave properties from our model. By doing this iteratively for different regions in space, what we got is this result. Here you are looking at the ECH wave-induced precipitating flux in the color scale, shown in this polar distribution, as if you are looking at the Earth from the North Pole. The circles are contours of magnetic latitudes, and these lines are the magnetic longitudes. The color, as we said, that is our model, the precipitation flux directly related to the ECH wave scattering. And interestingly, we want to verify or validate this result, right? So we compare it with the previous empirical models of the diffuse aurora, which is plotted in this panel in a similar fashion. So first we can see that these two share very similar spatial distribution in terms of latitudinal range and flux level. If we take the ratio of this one versus this one, what we can get. It's actually, interestingly, this is the contribution of ECH waves to the diffuse aurora in a general sense, right? So we can see that, this panel plots this ratio in a similar format as previous two panels. So this basically quantifies how much of this diffuse aurora precipitation comes from ECH wave scattering. So we can see that this ratio actually goes to about above 80% for majority of the high latitudes, especially at greater than 66 or 67 degrees. What this means, this just indicates that the ECH waves are the dominant driver of diffuse aurora at these high latitudes. So just to summarize it up, so we directly solved this long-standing problem about the origin of diffuse aurora by directly modeling the wave-particle interaction process, and it indicates that the ECH wave is the dominant driver of this precipitation in the higher latitudes, right? And then in addition, as I said that because our model, the precipitation, shared a very similar distribution with previous empirical models, this part of work also serves as a validation for our proposed precipitation model. And also this precipitation model is actually in line with one of my NASA grant to build a more realistic precipitation model and a conductance model from these wave sources. Yeah, I just want to mention this, very relevant to what I plan to do here. Okay. In addition, because our model will be parameterized directly by the fast plasma flows and plasma injections, it can be, versus previous models with solar wind conditions, right? It can be directly applied to global MHD models. That's the advantage of our model in terms of applicability, right? And specifically as for contributions to COSIA, because our diffusion codes are, what's the word? Are well established, but it can easily incorporate realistic magnetic field topology and density distributions along the magnetic field lines, so that the resulting conductance model will naturally include any interhemispheric asymmetry. Yeah, so this can potentially explain the asymmetries we observe in the magnetosphere. So that is not built on any assumption or something else. Yeah. Then let's talk about the third part, which is about the modulated Whistler waves by another mode called ultra low frequency perturbations in our magnetosphere. First, what is modulated Whistler waves at all? So this top panel shows an example of this quasi-periodic wave emissions in the Whistler wave frequency range. We call this modulated Whistlers is relative to this regular, more continuous wave emissions we usually observe in the radiation belt. Why do people care about this? It's because of this. It has been shown that this periodic wave amplitude, which is shown red here, is well correlated with the aurora intensity in conjunction with the ground measurements. So this modulated Whistler waves is a potential driver for the pulsating aurora, as we know from previous studies. But although there are a lot of studies devoted to this topic, but it has not been fully understood how this process is going in space. So our motivation here is to quantitatively understand or to quantify this process so that we can model it, or we can incorporate it into our model in the future. Yeah. So here is an example of Whistler wave observations in this panel in the down flank of the magnetosphere from the SEMIS observations. As shown in the top panel here, the black line is the, sorry about the notation. The black line is the fluctuations of magnetic field. The red line is this electric field fluctuations at a period of about 5 minutes, which we call the ultra low frequency waves, UF waves for short, as marked here. As this presence of the UF waves, we can see, interestingly, the electron distributions in this panel are also modulated by these UF waves. The black line is just the same as this one for the UF waves. And we see that this electron anisotropy basically is what we call this specific distribution of these electrons are also modulated by the UF waves. As a result, that we see the Whistler waves are also periodically showing up and on and off according to different phases with respect to this UF wave magnetic field fluctuation. So that's the process we wanted to understand. Our working hypothesis is that the UF waves modulate the electron distribution And this kind of variation in the anisotropy works as a potential source to generate this waste amount of waves. Yeah, that's our working hypothesis. Let's look at the model result. Yeah, so this is our model result. What we do is that we model the electron distributions in the presence of UF waves by preserving their first and second adiabatic invariance. So what we got is this, the black line is the same as before for UF wave fluctuations. So we can see that we can model it pretty well, that the electron distribution are consistent with what we see in observations. So it's the electron anisotropy level. So after we pass this model, the electron distribution, into our wave growth rate calculator, we got this periodic positive growth of the Whistler waves, which actually is corresponding to the periodic wave emissions in the observations. So overall, we can see that we have a pretty good modeling of the electron distribution, the electron anisotropy, and the wave growth in a way that's very consistent with the observations. So in a way that this confirms our understanding is right, our working hypothesis is right, so that we can have more confidence to incorporate this process into our future precipitation model. You may wonder that why do we care about this process? Because it sounds like it's such a minor addition to this wave scattering process. As shown in the right-hand side plot, this is the distribution of plasmas in the T perp over T parallel domain versus parallel electron beta domain. You don't need to care about these exact parameters. Let me just explain it to you. This black line here is basically the threshold for the Whistler wave intensity. The color-coded is the number of data points from real spacecraft observations. So we can see that towards this side it means that the plasma is unstable to Whistler wave generation. Of course, we can see in reality, most or majority of this plasma are marginally stable to the Whistler wave generation, which means that they cannot generate Whistler waves by themselves naturally. And here comes the UF waves. The UF waves actually can modulate the electron distribution in a way that to make them cross this threshold to give rise to the Whistler wave generation, at least periodically, right? So that subsequent electron scattering can follow from this newly generated Whistler waves. This is actually why we care about this modulation process, because it actually provides a new chain of energy transfer from UF waves to the energy input for the ionosphere, or the ionospheric properties in general. Yeah, that's pretty much it for the third part. Let's summarize it. So first of all, we quantify the process of the Whistler wave generation by the UF waves. We show it convincingly that the UF waves can indeed trigger the quasi-periodic Whistler wave generation, so that we can hopefully in the future incorporate this process into our precipitation model. And secondly, since we know that UF waves can occupy quite a large MLT sector, or quite a large spatial region in the magnetosphere, so if they can modulate or generate these Whistler waves in a large region, it means that they can result in electron precipitation and diffuse aurora in a very in a global scale, right? As opposed to the very confined spatial region by the nominal Whistler waves. So actually, this chain of UF wave driving Whistler waves, and then followed by the precipitation, can drive quasi-periodic variations in the magnetosphere and also in the ionospheric point of view. This part of work is also supported by two of my NASA grants, one as PI and one as co-I. Yeah, so that's why I'm also interested in continuing on this line of work. And of course, in terms of contribution to CUSIA, because the solar wind turbulence, let's take a step back. the solar wind turbulence is an important source for the UF waves. This chain of precipitation from solar wind turbulence to UF waves to Wessler waves and then to the precipitation that we established in this work can actually serve as an important media for the energy transfer from the solar wind transients to the ionosphere. So why does it important to COSIA? We will incorporate this UF wave-driven precipitation into our new conductance model to make it more realistic, because ignoring this part of process will probably underestimate the precipitation level from nominal Wessler waves, as we can see. And that's pretty much it for the main results that I wanted to cover in today's presentation. Then let's look out for the future. First of all, I want to mention that all this wave-particle interaction process we talked about previously, or a moment ago, can include the south-north asymmetry because this asymmetry comes from the magnetic field and density profile, the asymmetry from the magnetic field and density itself. So our wave-particle interaction process can naturally incorporate this asymmetry as well. And what will this asymmetry result in terms of magnetosphere and ionospheric coupling? That's what I want to discuss next, mainly from the three aspects. First, the electron scattering rates, as we discussed in the second part of work, depends on the energy distributions along magnetic field lines. That's what we call the density model or whatever you want. This kind of density distribution actually has been shown in the observations that we do see evidence that the density in two hemispheres can be asymmetric depending on the season, of course. And this can result in different diffusion rates and precipitation rates in the two hemispheres. Basically in the ionosphere of the two hemispheres. And this part of asymmetry, in terms of density asymmetry, has not been considered or incorporated into the wave-particle interaction models. But this density asymmetry, this kind of more realistic and asymmetric density distributions is what we can get from this global MHD models. So that interestingly, we can incorporate these two and get a more realistic diffusion rate and then precipitation rate out of it. The second aspect is that not all the precipitating particles will get lost to the ionosphere. This is probably too much details for, but I will briefly mention it because why is it so? Because many particles are actually reflected and scattered back to the magnetosphere because of colliding with the ionospheric particles. And so this reflection process actually determines how much of precipitation actually goes into this ionosphere. So interestingly, this reflection coefficient, as shown in this x-axis, depends on the altitude of which where the particles get lost. And this altitude is actually a profile of different densities. So in other words, the density profile will determine actually the backscatter threshold or backscatter coefficients of the particles. So naturally, because of density can be asymmetric in two hemispheres, so is this backscattering coefficient. So what does this mean? That it means that even with symmetrical scattering in two hemispheres, we will probably end up with different energy flux input in the two hemispheres because of this difference in the reflection coefficients or backscatter coefficients. That's the other aspect. The third one is that the wave propagation is controlled, as shown here by the background density and magnetic field distribution, magnetic field intensity basically, along the magnetic field lines. So the asymmetries in the density and the magnetic field would also result in asymmetries of in the wave propagation. And the wave propagation will also affect the wave power distribution in the two hemispheres in a more general sense. This kind of asymmetric distribution of the wave power in two hemispheres are actually measured by spacecraft transiting different hemispheres, but it has never been included into models of wave-particle interaction. So this part of work we can probably pursue more with the new modeling efforts in this department. Yeah, these are the three drivers of asymmetry we just talked about. Then what consequences do these asymmetries have? First is the asymmetry in the precipitation will directly drive an
participant is now joining.
Sorry, there's somebody talking here. Will directly drive an asymmetry in the conductance model. And the second, asymmetry in the precipitation and ionospheric temperature will result in a field-aligned electric field. And actually, this electric field will drive new instabilities in the background plasma and give rise to additional wave generation in the inner magnetosphere. This kind of coupling process has never been looked at carefully. That's what we can do with the capability here. And the third is that the asymmetries of precipitation trigger the asymmetries in the plasma outflow from the ionosphere. And why does this ionospheric outflow matter? Because it can change the low plasma density as well, and the low plasma density
participant is now exiting.
Sorry,
Don't
the
worry.
low density.
That's just somebody, if somebody comes in by phone or leaves by phone, the system does that automatically. So don't worry about it.
Yeah, it's just a very, overwhelming sound.
Yeah, a little disconcerting, but yeah, go ahead.
Yeah, sure. Why is the low density important? It's because it controls the local alpha speed. And the local alpha speed is relevant related to the reconnection rate. It's a long loop, I know. And so that's why this kind of asymmetry in the outflow can matter significantly to the magnetospheric activities. Actually, the spacecraft observations have shown evidence of this interhemispheric asymmetry in the plasma, this ionospheric outflows as observed in the plasma lobes, actually. But this effect, as I said, has not been incorporated or included into the magnetotail reconnection simulations. This is one potential aspect that we can improve on. And next, I would like to spend a couple more minutes to briefly talk about our new conductance model supported by the NASA grants in our project. Basically put an emphasis on the asymmetry of the conductance model. Here is what we try to do. A more realistic, eventually we want to achieve a more realistic conductance model in the next couple of years, as funded by our NASA grants, of course. This is the timeline we need to have. The way we do it is to model this wave-particle interaction process that directly drive the precipitation at the source. Here's what we will do it, how we will do it exactly. First, using the SEMIS and MMS measurements, we will build empirical models of the waves in response to the, say, plasma flows and injections in the magnetotail. And then we can pass these relationships to our wave diffusion code to estimate the precipitating electron spectra as a result of wave-particle interaction by each of these wave modes. Eventually, we will achieve these two additional wave modes as well. But today we will mainly talk about these two. So precipitating spectra as a function what we will get in this model is precipitating energy spectra as a function of energy and ionospheric location. And we will, parameterize this precipitating flux as a function of, this is magnetospheric activity level in the conjugate magnetosphere, and also parameterized by the turbulence level and also the MF electric field in the solar wind. Let me briefly talk about the advances of these two parameters. Is that first of all, as I said, that by including this, by parameterizing the precipitation directly to the magnetotail dynamics, either fast flows or the depolarization front or plasma injections, they are all related actually. We can directly apply this new model into the global MHD simulations, which directly produce these two quantities, so that we have a direct streamline to apply it to the models. And in addition, why do we want to parameterize the model with not only the average, not only by this MF electric field, but also this turbulence level in the solar wind? Is that because this we showed before, right? The turbulence determines the UF wave amplitude in the magnetosphere, and this UF wave can drive additional precipitation in the magnetosphere, so that we can directly parameter this chain of precipitation using this parameter called the solar wind turbulence. Yeah, that's pretty much the advantage of this model. And then eventually, of course, we wanted to convert it to the ionospheric conductance using this. This is how we propose it in our proposal. But we can certainly improve it if needed. We will we'll calculate the conductance out of this precipitating energy spectrum using this empirical formula built by Robinson et al. In earlier works. But recently, we can also incorporate more recent formulas to have a more realistic energy spectra of these particles incorporated into this conductance model. Yeah, it's probably too much details here, but let me give you a big picture here. On the left, this one is the computational scheme I got from Dan Welling about the CUSIA Center that they try to build here. So here is our new conductance model. How these two can be related is what I wanted to mention or emphasize here, because this conductance model can directly serve as input for this three connections between different models. So it can give rise to a more realistic electric potential that maps to the magnetosphere. And also, as I said, that this conductance model from our work will implicitly incorporate any interhemispheric asymmetry, so that it can directly resolve or explain these asymmetries from inner magnetosphere dynamics or from the other magnetospheric phenomena. So I think that's pretty much it. At the end, I just wanted to emphasize that our model is. I don't want to do it too much. Like our model indeed has some advantage by directly being parameterized by the magnetotail dynamics and the solar wind conditions, so that it's more applicable to the global MHD models as used in the CUSIA, and also that it intrinsically includes this interhemispheric asymmetry in the precipitation, so that we can more realistically simulate all the processes related to this interhemispheric asymmetry. Yeah, sorry for taking this long, but that will be all I want to cover. If you have any questions or comments, I would be happy to take them now. Thank you.
Well, thank you very much. Let me see who's got their hands up. So I see that Dan Welling has his hand up. So go ahead, Dan.
Oh, I can't unmute. There it goes. I'm sorry. It wouldn't let me unmute there for a second. So I have a question. You showed that comparison between your new precipitation model and an existing empirical one. I just had like a couple of quick questions on that comparison. I might have missed it, but what was the empirical model you were comparing to, and how is that one built? What does that one use as input data?
Okay, yeah, sure. This one is, I suppose you are talking about this slide, right? Yeah. This one is called the Ovation Prime model built by Newell et al. Yeah. So this model is an empirical model based on statistical data sets from the DMSP satellites, which directly measure the precipitating energy flux from the diffuse aurora perspective. Yeah, this one only incorporates the diffuse aurora. So what they do is that they parameterize this intensity of diffuse aurora in each of these locations, basically each of these bins, with solar wind inputs. They have a so-called solar wind coupling function to parameterize the intensity of this precipitation in each of these locations. So then they give a more empirical relationship. Yeah, but it's based on statistics. So yeah.
So do you have? I know this is still early days for the for your model, but what are the validation plans going forward? Or, for example, are you going to compare to, for example, DMSP or SUSY measurements or other sources of data to try to get comparisons to directly to observations? And if so, one more small part to that is, you're showing here the ratio between the two, but do you have any other metrics or ways to quantify the comparison in your head? Because 2D data can always be pretty tricky.
Okay. Yeah. First of all, in terms of validation, I'm not sure whether how do I put it? I'm not sure whether you are aware of it, but like for the ETH wave induced precipitation, there are already a couple of case studies directly comparing this ETH induced precipitation level with this aurora intensity in conjugate out-sky imagers, for example. So that this kind of work in this kind of work conducted by Binbin Yi previously in our group, that he has shown that this precipitating flux agrees quite well with this aurora intensity as observed in the conjugate imager. So that serves as an validation for sure. And then on the second perspective is that we hope this kind of statistics in our work will also serve a validation to our model here. And of course, that in the proposal, we also propose to validate the result with a couple more conjugate events between DMSP and STEMIS. So we're not that we haven't done that part yet, yeah. But the statistical the precipitation from the statistical wave properties have already been finished, yeah. And your second question is how to quantify this ratio, right, of this precipitation, contribution from ETH waves to the overall diffuse aurora, right?
Yeah.
Sorry, I didn't include it here, but we do have a line plot in addition to this 2D distribution. I think for this diffuse aurora precipitation itself, that we show about more than 50 or close to 60% of energy comes from these higher latitudes. And especially considering that these higher latitudes map it to the ionosphere at about greater than 8 RE. So that's the region where Whistler waves cannot be easily generated without injections. But these ECH waves can be almost semi-permanently there because they're different generation mechanism. Yeah. In short words, it's just that we showed more convincingly in the line plot that the ECH wave play a more dominant role for the diffuse aurora precipitation in the higher latitudes. Yeah.
Excellent. Thank you.
Yeah, sure.
Any other questions? Well, while I let the audience think about a question, I have a question.
Mm-hmm.
The last part of your talk, you put out this chain of events where solar wind turbulence results in higher levels of ULF waves in the magnetosphere. Then those ULF waves modify the electron distribution in the inner magnetosphere, pushing some electron distributions into the unstable regime where they generate Whistler waves, which then cause electron precipitation.
Yes.
Now, it's been well established that ULF waves are also driven by solar wind velocity, because velocity shear on the flanks of the magnetosphere causes boundary waves from the Kelvin-Helmholtz instability, and that produces ULF waves that get into the inner magnetosphere, so they should have the same effect. Has anyone demonstrated a link between the level of background Whistler waves and wind velocity? Evidence of that kind of a link?
Yeah, that's a very good question. Yeah, I'm aware that the solar wind velocity, especially the velocity shear, can serve as an additional source for driving the UF waves. But specifically, what we are talking about here, I didn't mention it because it's too much details. I figure it's too much detail, but I probably should. This particular wave mode we are interested in here is called compressional mode, compressional UF waves, which means that the main magnetic field fluctuation is along the background magnetic field line. So this kind of specific mode of waves is what we are interested in. So I'm not sure whether there are some empirical studies relating directly to the solar wind velocity, but what we are trying to achieve here is more or less more general sense of this turbulence, incorporating all the mesoscale transients in the solar wind. Because as we know that the previous models about the probably you know this better as an expert, that the previous models on the coupling between the solar wind and the magnetosphere is more on the average conditions of the solar wind, right? So what we found out in recent data is that the the mesoscale transients such as like high-speed magnetoshift jets and the foreshocks, these kind of things can have an impact on the magnetosphere in terms of driving these compressional UF waves. So that's what we want to incorporate it in this chain of precipitation. Yeah.
Okay, thank you. Let me see if there are any other raised hands. Yes, Yue.
Oh, hi. And nice talk. Thank you. I just have a quick question. You mentioned about the nonlinear wave particle induction is important. And so if we want to include that nonlinear process, do you need to make any change in your diffusion equation or not?
Oh, yeah. Yeah, let me try to get it more to my backup slide. Yeah, this one. Yeah, I didn't include it here because I figure it's too intimidating. Yeah, so actually that's a good question because incorporating the nonlinear effects is one of the ongoing efforts in our grants. In our projects. Yeah, but this is more like a long the long time scale projects because the top one is called linear diffusion equation that we normally use in existing radiation belt models. And in order to incorporate this nonlinear scattering and nonlinear trapping, what we need to do is to quantify these drift terms and this transport operator related to this nonlinear scattering and trapping process. And this one will require some theoretical efforts to incorporate observe the intense Whistler waves properties, such as the intensity, the wave frequency, into these operators. So that's an ongoing effort, but it has not been done. Sorry, but eventually, what we want to achieve is this kind of formula. It's similar to the first one, but more generalized by incorporating this additional terms that comes from the nonlinear effects. Yeah. So because I just wanted to make an addition to this line of discussion, is that currently the nonlinear model can do is just only model the particle dynamics resulting from these nonlinear effects in a very short time scale, say like a few bouncing period of these energetic particles. But as we know that the particle dynamics can change on the time scale of minutes or hours, right? So we need to do this in a long time scale. But the current simulation, which we call the test particle simulation, is actually tracing each individual particle. We cannot afford to do it by tracing 1 million particles within like a few hours or days. So eventually we will need this more generalized diffusion equation. Yeah, that's an ongoing effort.